you should remember that there are energy levels inside the atoms, and when the atom does some kind of transition because of the movement of the electron between different energy levels, it's going to emit or absorb different frequencies. Here we have a hot body. When you refract the light here, you see a continuous spectrum. If it goes through a cloud of cooler gas, some lines are going to be absorbed. Certain frequencies are going to be absorbed, corresponding to certain energy changes in this cloud of gas. These same energy changes will actually emit photons with a certain frequency, which is going to cause an emission line spectrum. Remember that E is equal to HF. The frequency is dependent on the energy transition. And this is basically an energy ladder. And one of these colors here, the red, in this part of the spectrum, this corresponds to an energy transition from n is equal to 3 to n is equal to 2. This energy difference will produce a photon, which will be emitted here. This is part of the emission line spectrum. So we see only certain frequencies, which means only certain energy jumps or transitions, and therefore there must be only certain energy levels. In other words, energy is quantized in atoms. We have to describe one piece of evidence for the existence of nuclear energy levels. So not only is energy quantized in atoms, it's also quantized within the nucleus. When we look at gamma ray emission, which comes from the nucleus, we notice that only certain frequencies are emitted. These frequencies, E is equal to HF, correspond to discrete energy transitions inside the nucleus. And these correspond to transitions between discrete energy levels, just like the electron in the atom. Alpha decay, alpha particles also, when they are emitted, only have certain discrete energies, only certain values. These energies correspond to discrete energy transitions from inside the nucleus, exactly the same as the gamma ray. So what is the conclusion? The conclusion is that the nucleus must have discrete energy levels. In other words, is quantized, just like the electron energy levels inside the atom. So we have the gamma, alpha, and the next is beta decay. What happens with beta decay? Well, one would expect that also to have certain energy levels. So the beta decay should have discrete energies corresponding to the transition between discrete energy levels inside the nucleus. However, unfortunately, it didn't work out that way. The beta particle had a range of energies, continuous range, and this conflicted with this quantized idea of the nucleus, which said that beta particles should have discrete energies, only certain energies corresponding to only transition between certain energy levels inside the nucleus. So it's a bit like this. You would expect an alpha particle to go from E2 to E1, because let's say this is a difference. This is a transition between two energy levels, and that is delta E. And you would expect the same for alpha particles, and you get that. And you expect the same from beta particles. But no, it doesn't work out that way. With a beta particle, there would be any range of values that it could come out with between E2 and E1. Then let's say that it only goes this far. And this is one rung on the energy ladder, this is the next rung on the energy ladder. How is it possible that this energy could be released, only this amount of energy? What about the rest in that jump? So there's some energy missing. So let's say this is a beta particle that has been emitted with this amount of energy, but it should be this amount. Where could this energy be going if it were quantized? Physicists were so confident of this that they said there must be something else, something very small, something very neutral, which is taking away some of that energy to make it up to the full value for the delta E, the full transition between E2 and E1, for example. It's going to be very difficult to detect it directly because it's got no charge and it's also very small. So it's got no charge, so they used the word neutron. They first described it as a neutron, but then shortly afterwards, a big particle in the nucleus had been discovered that was called the neutron. But this was much smaller than a neutron, so they called it a small neutron, or in other words, a neutrino. In fact, in this beta decay, an antineutrino is produced, but the idea was that it was a small neutral charge, this small neutral particle called a neutrino. So, describe beta plus decay, including the existence of the neutrino or the antineutrino. Let's look at beta decay. The neutron decays into proton plus a beta particle, but we know this is not all the energy. Something else is carrying the energy as well, because this is not necessarily going to be the full transition, because it has a continuous range of energies. What happens when it doesn't match the recognized energy trend? There must be something else that makes up the energy, and this is called the anti-neutrino. And there we have, it's like a V, it's a Greek V with a subscript E, which means it's paired with an electron, and a bar over the top means it's an anti-neutrino. So the beta decay has a continuous range of energies, and is conflicted with the quantized nucleus, which said that the beta particles should have discrete energies. So this was the prediction of the antineutrino done, which was made by Wolfgang Pauli in 1930. But it was actually discovered some 26 years afterwards, and the people that discovered it actually got the Nobel Prize for Physics in 1995. This is not a mistake. They did this discovery in 1956. They were given the Nobel Prize for this 40 years afterwards. Okay, occasionally also, we'll go on to the next thing, which is instead of a neutron turning into a proton and a negative beta particle, sometimes a proton will turn into a neutron plus a positive beta particle, also known as a positron as opposed to electron, and that would release a neutrino, not an antineutrino. A positron, which is a positive electron, is a antiparticle. Yes. And this is an evidence. This is a famous experiment which shows the measurement of a beta plus particle. You can see the path that it takes there. This is the line, this is a trace followed by the beta particle. You know it must be going in this direction because it goes through a metal plate here, and then it loses energy there, so its curvature is much sharper. So it's actually going from bottom upwards to the top part there. All this is in a magnetic field which is bending the path of the positron. This was made by this positron, this positive electron, this was discovered by Anderson in 1932. And BN means there's a magnetic field going into this. So how is this possible? So if you use Fleming's left-hand motor rule, you will know that it must be a positive particle because it's going in this direction and gets bent that way. The magnetic field is going into the paper, the current is going up because it's a positive particle, and therefore there's a force to the left. And this is the nuclear equation. A proton decays into a neutron and a positron and releases then neutrino. And here's an example of that. I think that's palladium. One of these protons, it's got a number of 91. One of these protons turns into a neutron, so this 91 is going to go down to 90, so it has one proton less. 230 is still the same because it still has the same number of nucleons, but it releases a beta plus particles. And there you have it.